Hi guys, and welcome back to another Tech Minds video. So if you saw the first part of my build a UHF amplifier from a commercial pallet video, well, this is part 2 and quite possibly the last part. So let's first go over what this amplifier does, and then for the most part of this video I'll show you how I got to this stage. Now, as we can see, the front panel has a 4-line LCD which is connected to an Arduino inside the case. Now, the LCD will show heatsink temperature, forward power and a dB value converted from that forward power. Line 4 on the LCD, the bottom line, is actually a bar graph which goes from left to right, and that should essentially show from 1 to 250 watts. There's also an SMA socket on the left, which is the RF input. Now for the test, I'll just be using an E200 ANTSDR, which outputs between 5 to 10 milliwatts at 437 MHz. Now this amplifier can take up to around 100 to 150 milliwatt for full output power, but for now I'll just be testing with a low power input, but more on that later. The code that's running on the Arduino is something that I've written with a little help from ChatGPT. Now ChatGPT really helped with the lookup table for showing a near accurate power level, but more work on this is needed in the future. Now where we left off on the last video, I just performed the hardware modification to the RF pallet and adjusted the bias controls according to the procedure that I was given. I did not record the whole process, but as you can see here, I started by trying to find a position to mount the pallet within the case that I brought. I also had to consider the low pass filter board, which incidentally I did create a whole separate video on how to construct it, so you can go and check that out if you want to. Now one of the things that I really wanted to show was forward power and reflected power on that LCD, basically showing the output RF in watts and then the calculated SWR. So I set about to make a bidirectional RF coupler. Now I did find quite a few designs online and even some boards you could purchase, but I decided to make my own. Now normally this kind of design with such high power in mind would require special PCB material, like the material that we use for the low pass filter. But Rogers PCB type is very hard to get hold of, at least in my neck of the woods. So I felt lucky when I come across this design on this website, where the designer had 2 FR4 type boards sandwiched together, and then they just widened the center track slightly to help with match and handle that more power. Now this design also provides forward and reflective power, and they also provided a simple circuit which provided a small DC voltage depending on the forward or reflective power. You just had to add a couple of components to the board to make that work. So I started designing the board layout and then used my Makera Carvera Air CNC machine to make the PCB. Now I absolutely love this machine and it's really changed the way that I work with homemade projects. If you can afford one, I would definitely recommend it. As I want to encase the whole coupler, I designed and cut out side panels and a lid, all made from that FR4 material, which is single-sided copper. Now I was really pleased to how this came out. It looked very neat and well made. So now it was time to assemble. Now I needed some way of holding the 2 FR4 boards together, so I just used rivets for this. First I drilled a hole, pushed them through and then tapped them together. Now as the side panels are made from FR4, I can just solder them in place. Now this might appear to be easier said than done, but it was actually quite fiddly to start off with. Once you have the first board in place, it does actually get easier as you solder the rest of them. Now you will notice that I've already attached N-type sockets to the end plates. Now if you do this, then I would suggest to tack the panels in place just in case you have to move them or shuffle them around a bit as you start adding the rest of the panels. However, once the sides are finally soldered on, I now soldered the rivets that I'd placed through the boards earlier. Now each of the coupled outputs should read as a 50 ohm match, I believe, but an 82 ohm resistor was actually needed. Now I made it this way so that I could use an external RF sampler instead of creating a DC output circuit directly on the coupler itself. But now I needed to test the offset, i.e. how much drop in dB each port has. So using my VNA, I could do this, and after testing, both ports observed around a 37 dB drop, which I was quite pleased about. With the coupler built, I now needed to do some more work on the case. Now where I wanted the N-type output socket to fit, it was just kind of a hole in the panel, so I ordered a sheet of aluminium from Amazon, designed a panel with the holes in the correct places, and then used my CNC machine to cut it out. Like I said earlier, having the CNC machine just makes life so much easier. I don't have to mess around with a hacksaw trying to cut it straight and make it look good. And well, this is what it looks like after it's been fitted. Now you also notice those heavy duty high current power terminals, and this is where we'll connect the power supply to it when we come to testing it. Now deciding where I was going to put everything took some time, and this is the first iteration of how I laid things out. Now this did work and it actually produced some nice output power, but I wasn't happy with the way some of the things was laid out. Like I didn't want to have such long cables and the RF sampler, so I made some changes. So let me show you those changes and go over each section. And I'd like to take a moment to thank JLC PCB for sponsoring this video. Now JLC PCB provide easy, affordable and reliable PCB and PCBA solutions, empowering electronic engineers to develop projects efficiently. Now JLC PCB website is extremely easy to use, and ordering PCBs from JLC PCB is effortless. Just simply upload your Gerber file to get an instant quote and place your order in minutes. It's as easy as shopping online. Now you can get 1 to 8 layer PCBs for just $2, and with efficient large-scale production, this reduces cost and brings you unbeatable prices. Quality and lead time is highly reliable, and all in-house production ensures quality stability, especially with their strict quality control in every process. You can have your PCBs produced in less than 24 hours if you need them in a rush. Easy to use, affordable to make, and reliable to trust. You can always count on JLC PCB. Now don't miss out JLC PCB's 6-layer PCB special. You can get $30 off with a coupon and enjoy top quality 6-layer PCBs for just $5. Thanks again to JLC PCB for sponsoring this video. So this is the inside of the box. Now I guess I'm going to have to give you some form of explanation of what everything does. Now it isn't 100% finished. There's still a couple of things that I want to do. So first off, we've got obviously the main pallet here. And what you might notice here is on this circulator, I've got some magnets here attached to it. Now the reason for that is because the passband for this circulator is 450 to 480 megahertz, and obviously we want to use this around 435 megahertz. So by putting these magnets on in place here, it kind of detunes that passband, which makes it more efficient for the frequency that we want to use. If you're not sure what a circulator does, well, technically, if it sees a high SWR or improper match on the output here, it will dump the RF output to this resistor here. This is a 150 watt resistor, 50 ohm. So it acts like a dummy load. So it protects these two final transistors, which is, and obviously the combiner. It will protect, which is quite good. It's very good. Now in terms of design, so over here we've got the low pass filter, which I did make a video on and showed you how I made this using my CNC machine, the Makera Carvera Air. Now what you would have noticed from the picture I showed you a moment ago is that I'm no longer using the bidirectional coupler that I made. And the reason for that really is because, not because it didn't work, it worked very well indeed. But I decided that I wasn't going to measure the reflected power. I think measuring the SWR I probably don't really need. I can add it back in if I want to, but I realised that there's a directional coupler already on the board here. So this is giving me my forward output. I'll talk more about this in a moment. The coax I'm using here is RG402 or SM141 to go between the output and the input of the filter and then the output which is over there on the back of the amplifier. I'll show you that in a moment as an N-type connector. Now you might see this looks a bit of a mess with solder. Yeah, what happened here was I originally built it with N-type sockets on this filter, which you would have seen in a previous video and up close as I built it. And I had a smart idea of like maybe I could actually solder it to the board here and just link. So there was actually a time when I soldered this board directly to here, to the output side, and fed it directly. However, the match wasn't great, so it was dumping most of the RF to the resistor here as opposed to going out. So by doing it this way, a short piece of 50 ohm RG402 coax, and then I get a lovely match. So I've actually, before I connected it to the board here, I put it on my VNA and done some measurements for SWR, etc. And the match is perfect. So we've got no issue with match between the output here and the filter. So you might be wondering what this sort of mess is around here. I did have a bit of an accident actually. I didn't realise, but these bits here across the middle of these, I think these are like protection fuses. I think it's grounded, and when I resoldered the power cable on, it was shorting it, and there's actually there was a ground strip going across underneath underneath here. There's a strip, and it obviously you can see here it's burnt it out. But anyway, it works fine. But it was quite amazing when I connected it up, because literally it was like a fireworks show. This literally, it was just popping out molten metal all over the place in these little beads. But luckily it done its job, it protected it, and it was just my fault where I'd over soldered this main power connector or wire into the power input here. It had shorted to the ground track, and I didn't realise that. But anyway, that's just that. It was a mistake. We all make mistakes, and luckily it didn't damage anything else on the board. So as I mentioned earlier, so we've got a directional coupler, and it's coming out here. Now I think this is around about a -40 dB. I then use a 20 dB attenuator, which then goes off to this little circuit over here. Now in here is an AD863.2, I think it is. Which might be a bit overkill for this. It's a very high resolution true power meter. So you've got RF going in, and then you get a DC voltage that comes out. Now when I first got this and installed it, I did think to myself, why on earth have they got an SMA socket for the output when it's a DC voltage? And then I realized it's actually kind of handy, because you can use screened coax or screened cable so that any RF does not get into the DC wires that are coming out here, which could potentially affect the reading. I mean, I know I've got a bit of an issue here, which I might have to sort out at another time. But let's just talk about how that works. So the RF goes out of here into here. So whatever comes out of here, we're looking at, say, -60 dB of whatever that is into here. Get a small voltage come out of here, and as the power output changes, so does the voltage. This is just a little circuit board that I designed in KiCad, and then just made on my CNC machine. If I've got any footage of that, I'll show you it now on the screen, but it was very easy to do, very easy to make. It was just a very quick knock up, just as a test really. I think I have got the scope or possibility to redo this board so that it's encapsulated like we saw with the directional coupler that I made earlier for this that I was originally going to use. But we've also got, so we've got an Arduino here, Arduino Nano, and that's basically what that's going to do is take the DC voltage from this power meter here. It goes into an ADS1115. This gives a higher resolution for reading the analog pins here, or measuring the voltage. It's probably overkill yet again. I could have just taken it straight into the Nano analog pin, but I was just kind of experimenting, so you know. There's as well as having the measurement for the RF power, I've also got here an NTC. It's just like a thermistor that comes over to here. This is essentially a temperature sensor. Now I might change this. I would like this to be a bit more accurate. I think it is fairly accurate as it is now, but I do have on order another temperature sensor which should be more accurate, which can still plug into or still be wired into the Nano. Now the Nano is actually connected to a 4-line screen, 4-line LCD, and you would have seen that at the start of the video. Now the power that comes into this whole amplifier is actually 28 volts. This pallet or RF pallet amplifier needs 28 volts. So there's a couple of other voltages that we need to consider. Now the whole Arduino system, including the power sensor, uses 5 volts. So over here we've got a step down Dubry Watsit, which you can then have 28 volts going in, adjust the pot here to give you 5 volts out. Now I've got another one over here which you may be wondering why I've got it. There's nothing connected to it at the moment. Well, that's because I have a fan which will go on top of the heatsink. It's quite a large fan. I haven't wired it up yet, but that will take between 12 to 15 volts. Running it at 28 volts, it's just going to run too fast and it's not designed for it. So I've got another one here that I haven't wired up yet. I have set the voltage on this, but I haven't actually wired it up. I will do that, and you may have already actually seen it on top working, depending on which way around this video footage goes out. The input into the amplifier, which is over here, it's a section here. Now it didn't have these SMA connections like the same with this one here. This is just an SMA socket kind of soldered onto the board, just so it's nice and easy to connect, and the same with this. Now this side, this is just SM141 or RG402. That just goes off to an SMA socket on the front. Now I chose to use an SMA socket purely because the input power on this doesn't need to be a lot. I've run it with 10 milliwatts and get way over 100 watts output, which is fantastic. I could probably go up to about 100 milliwatts to get the full power out of it, but unfortunately I don't have a power meter and I don't have a dummy load or antenna that can handle more than 200 watts, unfortunately. So I'm a bit limited to actually give this a proper stress test to see how much power this whole thing can do. I think I'm going to have to invest in a higher power dummy load and a higher power power meter for sure. So I think that's pretty much it. If you've got any questions on this, then let us know down in the comments below. But I think it's now time to move on to the next section of the video. Now, as this amplifier will primarily be used for DATV, that's digital amateur television, I performed some tests using an application called DATV Easy. Now this is connected to the E200 SDR over Ethernet, and it transmits a DVB S2 signal with a 333 kHz symbol rate. Now remember that the E200 is merely outputting a few milliwatts here, and already my power meter winds up over 100 watts. However, the power meter on the right here is probably designed for use with FM, AM and SSB in mind, not wideband digital signals, so the reading here could be a little off. The power sensor, however, that I'm using in the amplifier is actually designed to work with digital signals. So one of my future plans is to set up a test procedure to calibrate the power meter shown on the LCD to the best of my ability. Something like this, it really only needs to be in a ballpark figure anyhow, but it's nice to get it as accurate as possible. Now I know some of the Spectrum police like to comment on these types of videos if I miss something important, and one of the most important things to check when creating amplifiers is measuring the spurious emissions. Well, look at this. With a minus 26 dB input, which is the recommended input for the Tiny SA's dynamic range at 437 MHz, there's literally no harmonics, or none that are above minus 75 dB. So I think the low pass filter that we made and used in this amplifier is doing a great job. Now if we take a look at a nearby SDR to see how smooth that DATV signal is, or take a look at any shoulders, well, take a look at this. It's super clean, even pushing it around 100 watts. So I think this amp will work great for my use on digital amateur television. Now if you're wondering what the big black heatsink is underneath that NISSEI power meter, well that's my makeshift 250 watt dummy load. Now I do actually have a USB power meter which appears to be quite accurate even with the digital signals, but I need to source a hefty attenuator which can handle up to 300 watts. Obviously I don't want to put 300 watts into my USB power meter. Now I do also have a great little driver board to bring the input up to around 100 milliwatts if needed, so I can then test the full power of this amplifier. But I really want to get the correct test equipment in place before I really push this amplifier. Now the 100 watts that I can already get out of this amplifier is already way too much for actually what I need to use it for, but it will be nice to get it working to its full potential in case in the future I need a bit more power. One other thing to mention, and that's the electronics, like the Arduino etc. that's inside the box. Now I may possibly encase these in FR4 to shield it, but I have actually put mini ferrite beads on some of the cables. Not sure if you saw those, but the important part for me was the power sensor. Now I know there's a little bit more work to do, but so far so good. Not sure if I'll make any more videos on this as it's pretty much there already. I just need to cover a little bit more on the calibration once I'm able to test the output properly. Anyway guys, thanks so much for watching. If you guys have got any comments, any suggestions, then please put them down in the comments below. I'll be very interested to hear what you have to say. Again, I'm not an expert on this. This is just me having a bit of fun and trying not to blow myself up. Until the next video, take care of yourselves and I'll see you in the next video.